Alrighty then. So I have two more physics and business to do, and I'll do some Bible readings, and then um, probably just go ahead and go into chapter 2 of biology. I'm going to do a bunch of OpenStax and a bunch of Bible stuff today. I really need to go back to work, but it was not a good morning this morning, so I've decided to take it easy again. Tomorrow I should be good to go. I'm not going to eat any more for the rest of the day. um, I'm just going to drink water. I still have a half gallon left, so that should cover me for the rest of the day. Yeah, we'll see where that goes. All right. So let's go ahead and swap to Rhinestone 2. So this will be 6, 6. There we go. All right, let's go ahead and read some physics. I'll have to pause for a minute once the cycler sets up. There should be no problem there. Okay. Back. Science. University physics. Download. Go. Okay. Chapter 1, Units and Measurement. Let's close that. Okay. Chapter outline. The scope and scale of physics, units and standards, unit conversions, dimensional analysis, estimates and Fermi calculations, significant figures, solving problems in physics. It's actually going to be really similar to chemistry. Introduction. As noted in the figure caption, the chapter opening image is of the Whirlpool Galaxy, which we examine in the first section of this chapter. Galaxies are as immense as atoms are small, yet the same laws of physics describe both, along with all the rest of nature, an indication of the underlying unity in the universe. The laws of physics are surprisingly few, implying an underlying simplicity to nature's apparent complexity. In this text, you learn about the laws of physics. Galaxies and atoms may seem far removed from your daily life, but as you begin to explore this broad-ranging subject, you may soon come to realize that physics plays a much larger role in your life than you first thought, no matter your life goals or career choice. 1.1. The scope and scale of physics. Learning objectives. By the end of this section, you will be able to describe the scope of physics, calculate the order of magnitude of a quantity, compare measurable length, mass, and time scales quantitatively, describe the relationships among models, theories, and laws. Physics is devoted to the understanding of all natural phenomena. In physics, we try to understand physical phenomena at all scales, from the world of subatomic particles to the entire universe. Despite the breadth of the subject, the various subfields of physics share a common core. The same basic training in physics will prepare you to work in any area of physics and the related areas of science and engineering. In this section, we investigate the scope of physics, the scales of length, mass, and time over which the laws of physics have been shown to be applicable, and the process by which science in general and physics in particular operates. The scope of physics. Take another look at the chapter opening image. The Whirlpool Galaxy contains billions of individual stars, as well as huge clouds of gas and dust. Its companion galaxy is also visible to the right. The pair of galaxies lies a staggering billion trillion miles from our own galaxy. The stars and planets that make up the Whirlpool galaxy might seem to be the furthest thing from most people's everyday lives, but the Whirlpool is a great starting point to think about the forces that hold the universe together. The forces that cause the Whirlpool galaxy to act as it does are thought to be the same forces we contend with here on Earth. Whether we are planning to send a rocket into space or simply planning to raise the walls for a new home, the gravity that causes the stars of the Whirlpool galaxy to rotate and revolve is thought to be the same as what causes water to flow over hydroelectric dams here on Earth. When you look up at the stars, realize the forces out there are the same as the ones here on Earth. Through a study of physics, you may gain a greater understanding of the interconnectedness of everything we can see and know in this universe. Think now about all the technological devices you use on a regular basis. Computers, smartphones, global positioning systems, MP3 players, and satellite radio might come to mind. Then think about the most exciting modern technologies you have heard about in the news, such as trains that levitate above tracks, invisibility cloaks that bend light around them, and microscopic robots that fight cancer cells in our bodies. All these groundbreaking advances, commonplace or unbelievable, rely on the principles of physics. Aside from playing a significant role in technology, professionals such as engineers, pilots, physicians, physical therapists, electricians, and computer programmers apply physics concepts in their daily work. For example, a pilot must understand how wind forces affect a flight path. A physical therapist must understand how the muscles in the body experience forces as they move and bend. As you will learn in this text, the principles of physics are propelling new, exciting technologies, and these principles are applied in a wide range of careers. The underlying order of nature makes science in general, and physics in particular, interesting and enjoyable to study. For example, what do a bag of chips and a car battery have in common? Both contain energy that can be converted to other forms. The law of conservation of energy ties together such topics as food calories, batteries, heat, light, and watch springs. Understands this law makes it easier to learn about the various forms of energy takes and how they relate to one another. Apparently, unrelated topics are connected through broadly applicable physical laws, permitting an understanding beyond just the memorization of lists of facts. Science consists of theories and laws that are the general truths of nature, as well as the body of knowledge they encompass. Scientists are continuously trying to expand this body of knowledge and to perfect the expression of the laws that describe it. Physics, which comes from the Greek physis, meaning nature, is concerned with describing the interactions of energy, matter, space, and time to uncover the fundamental mechanisms that underlie every phenomenon. This concern for describing the basic phenomena in nature essentially defines the scope of physics. Physics aims to understand the world around us at the most basic level. It emphasizes the use of small number of quantitative laws to do this, which can be useful to other fields pushing the performance boundaries of existing technologies. Consider a smartphone. Physics describes how electricity interacts with the various circuits inside the device. This knowledge helps engineers select the appropriate materials and circuit layout when building a smartphone. Knowledge of the physics underlying these devices is required to shrink their size or increase their processing speed. Or, think about a GPS. Physics describes the relationship between the speed of an object, the distance over which it travels, and the time it takes to travel that distance. When you use a GPS in a vehicle, it relies on physics equations to determine the travel time from one location to another. Knowledge of physics is useful in everyday situations as well as in non-scientific professions. It can help you understand how microwave ovens work, why metals should not be put into them, and why they might affect pacemakers. Physics allows you to understand the hazards of radiation and to evaluate these hazards rationally and more easily. Physics also explains the reason why a black car radiator helps remove heat in a car engine, and it explains why a white roof helps keep the inside of a house cool. Similarly, the operation of a car's ignition system, as well as the transmission of electrical signals throughout our body's nervous system, are much easier to understand when you think about them in terms of basic physics. Physics is a key element of many important disciplines and contributes directly to others. Chemistry, for example, since it deals with the interactions of atoms and molecules, has close ties to atomic and molecular physics. Most branches of engineering are concerned with designing new technologies, processes, or structures within the constraints set by the laws of physics. In architecture, physics is at the heart of structural stability and is involved in the acoustics, heating, lighting, and cooling of buildings. Parts of geology rely heavily on physics, such as radioactive dating of rocks, earthquake analysis, and heat transfer within Earth. Some disciplines, such as biophysics and geophysics, are hybrids of physics and other disciplines. Physics has many applications in the biological sciences. On the macroscopic level, it helps describe the properties of cells and their environments. On the macroscopic level, it explains the heat, work, and power associated with the human body and its various organ systems. Physics is involved in medical diagnostics such as radiographs, magnetic resonance imaging, and ultrasonic blood flow measurements. Medical therapy sometimes involves physics directly. For example, cancer radiotherapy uses ionizing radiation. Physics also explains sensory phenomena, such as how musical instruments make sound, how the eye detects color, and how lasers transmit information. It is not necessary to study all applications of physics formally. What is most useful is knowing the basic laws of physics and developing skills in the analytical methods for applying them. The study of physics can also improve your problem-solving skills. Furthermore, physics retains the most basic aspects of science, so it is used by all the sciences, and the study of physics makes other sciences easier to understand. The scale of physics. From the discussion so far, it should be clear that to accomplish your goals in any of the various fields within the natural sciences and engineering, a thorough grounding in the laws of physics is necessary. The reason for this is simply that the laws of physics govern everything in the observable universe at all measurable scales of length, mass, and time. Now that is easy enough to say, but to come to grips with what it really means, we really need to get a little bit quantitative. So before surveying the various scales that physics allows us to explore, let's first look at the concept of order of magnitude, which we use to come to terms with the vast ranges of length, mass, and time that we consider in this text. Order of magnitude. The order of magnitude of a number is the power of 10 that most closely approximates it. Thus, the order of magnitude refers to the scale of the value. Each power of 10 represents a different order of magnitude. For example, 10 to the 1, 10 to the 2, 10 to the 3, and so forth are all different orders of magnitude, as are 10 to the 0 equals 1, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. To find the order of magnitude of a number, take the base 10 logarithm of the number and round it to the nearest integer. Then the order of magnitude of the number is simply the resulting power of 10. For example, the order of magnitude is 800 is 10 to the 3 because log base 10, 800 is approximately 2.903, which rounds to 3. Similarly, the order of magnitude of 450 is 10 to the 3rd because log base 10 of 450 is approximately 2.653, which rounds to 3 as well. Thus we say the numbers 800 and 450 are the same order of magnitude, 10 to the 3. However, the order of magnitude of 250 is 10 to the 2, because log base 10 of 250 is 2.397, which rounds to 2. An equivalent but quicker way to find the order of magnitude of a number is first to write it in scientific notation, and then check to see whether the first factor is greater than or less than root 10, which equals 10 to the 0.5 power, which is about 3. The idea that root 10 equals 10 to the 0.5 is halfway between 1 equals 10 to the 0 and 10 equals 10 to the 1. On a log-based scale, thus, if the first factor is less than root 10, then we round it down to 1, and the order of magnitude is simply whatever power of 10 is required to write the number in scientific notation. On the other hand, if the first factor is greater than root 10, then we round it up to 10, and the order of magnitude is 1 power of 10 higher than the power needed to write the number in scientific notation. For example, the number 800 can be written in scientific notation as 8 times 10 squared. Because 8 is bigger than root 10, it's about 3, we say the order of magnitude of 800 is 10 to the 2 plus 1 power, which is about 10 to the 3. The number 450 can be written as 4.5 times 10 squared. So its order of magnitude is also 10 to the 3 because 4.5 is greater than 3. However, 250 written in scientific notation is 2.5 times 10 to the 2. And 2.5 is less than 3, so its order of magnitude is 10 to the 2. The order of magnitude of a number is designed to be a ballpark estimate for the scale of its value. It is simply a way of rounding numbers consistently to the nearest power of 10. This makes doing rough mental math with very big and very small numbers easier. For example, the diameter of a hydrogen atom is on the order of 10 to the negative 10 meters, whereas the diameter of the sun is on the order of 10 to the 9 meters. So it would take roughly 10 to the 9 divided by 10 to the negative 10, 10 to the 19 hydrogen atoms to stretch across the diameter of the sun. This is much easier to do in your head than doing the more precise values of 1.06 times 10 to the negative 10 meters for a hydrogen atom diameter and 1.39 times 10 to the 9 meters for the sun's diameter, to find that it would take 1.31 times 10 to the 19th hydrogen atoms to stretch across the sun's diameter. In addition to being easier, the rough estimate is also nearly as informative as precise calculation. All right, I'm going to pause for 1 sec. I need to grab that. Oh, okay. All right, connected. Dialysis time. Known ranges of length, mass, and time. The vastness of the universe and the breadth over which physics applies are illustrated by the wide range of examples of known lengths, masses, and times in Figure 1.4. Examining this table will give you a feeling for the range of possible topics in physics and numerical values. A good way to appreciate the vastness of the ranges of values in Figure 1.4 is to try to understand some simple comparative questions, such as the following. How many hydrogen atoms does it take to stretch across the diameter of the sun? Answer: 10 to the 9 meters over 10 to the negative 10 meters equals 10 to the 19 hydrogen atoms. How many protons are there in a bacterium? Answer: 10 to the negative 15 kilograms over 10 to the negative 27 kilograms equals 10 to the 12 protons. How many floating point operations can a superconductor do in one day? Answer: 10 to the 5 seconds divided by 10 to the negative 17 seconds equals 10 to the 22 floating point operations. In studying Figure 1.4, take some time to come up with similar questions that interest you and then try answering them. Doing this can breathe some life into almost any table of numbers. Building models. How did we come to know the laws governing natural phenomena? What we refer to as laws of nature are concise descriptions of the universe around us. They are human statements of the underlying laws or rules that all natural processes follow. Such laws are intrinsic to the universe. Humans did not create them and cannot change them. We can only discover and understand them. Their discovery is a very human endeavor, with all the elements of mystery, imagination, struggle, triumph, and disappointment inherent in any creative effort. The cornerstone of discovering natural laws is observation. Scientists must describe the universe as it is, not as we imagine it to be. A model is a representation of something that is often too difficult to display directly. Although a model is justified by experimental tests, it is only accurate in describing certain aspects of a physical system. An example is the Bohr model of single electron atoms, in which the electron is pictured as orbiting the nucleus, analogous to the way planets orbit the sun. We cannot observe electron orbits directly, but the mental image helps explain some of the observations we can make. such as the emission of light from hot gases. However, other observations show that the picture in the Bohr model is not really what atoms look like. The model is wrong, but is still useful for some purposes. Physicists use models for a variety of purposes. For example, models can help physicists analyze a scenario and perform a calculation, or models can be used to represent a situation in the form of a computer simulation. Ultimately, however, the results of these calculations and simulations need to be double-checked by other means, namely observation and experimentation. The word theory means something different to scientists than what is often meant when the word is used in everyday conversation. In particular, to a scientist, a theory is not the same as a guess or an idea, or even a hypothesis. The phrase, "it's just a theory," seems meaningless and silly to scientists because science is founded on the notion of theories. To a scientist, a theory is a testable explanation for patterns in nature supported by scientific evidence and verified multiple times by various groups of researchers. Some theories include models to help visualize phenomena, whereas others do not. Newton's theory of gravity, for example, does not require a model or mental image because we can observe the objects directly with our own senses. The kinetic theory of gases, on the other hand, is a model in which a gas is viewed as being composed of atoms and molecules. Atoms and molecules are too small to be observed directly with our senses. Thus, we picture them mentally and understand what the instruments tell us about the behavior of gases. Hold on. Ouch. Oh, I like that. Nope. There it is. So, sorry, I had a little ingrown little hairy. Looks like I think I got it though. Yep, I did. Nice. All right. The kinetic theory of gases, on the other hand, is a model in which a gas is viewed as being composed of atoms and molecules. Atoms and molecules are too small to be observed directly with our senses. Thus, we picture them mentally to understand what the instruments tell us about the behavior of gases. Although models are meant only to describe certain aspects of a physical system accurately, a theory should describe all aspects of any system that falls within its domain of applicability. In particular, any experimentally testable implication of a theory should be verified. If an experiment ever shows an implication of a theory to be false, then the theory is either thrown out or modified suitably. A law uses concise language to describe a generalized pattern in nature supported by scientific evidence and repeated experiments. Often, a law can be expressed in the form of a single mathematical equation. Laws and theories are similar in that they are both scientific statements that result from a tested hypothesis and are supported by scientific evidence. However, the designation law is usually reserved for a concise and very general statement that describes phenomena in nature, such as the law that energy is conserved during any process, or Newton's second law of motion, which relates force, mass, and acceleration with a simple equation F equals ma. A theory, in contrast, is a less concise statement of observed behavior. For example, the theory of evolution and the theory of relativity cannot be expressed concisely enough to be considered laws. The biggest difference between a law and a theory is that a theory is much more complex and dynamic. A law describes a single action, whereas a theory explains an entire group of related phenomena. Less broadly applicable statements are usually called principles, but the distinction between laws and principles often is not made carefully. The models, theories, and laws we devise sometimes imply the existence of objects or phenomena that are as yet unobserved. These predictions are remarkable triumphs and tributes to the power of science. If the underlying order in the universe that enables scientists to make such particular predictions, however, if experimentation does not verify our predictions, then the theory or law is wrong, no matter how elegant or convenient it is. Laws can never be known with absolute certainty because it is impossible to perform every imaginable experiment to confirm a law for every possible scenario. Physicists operate under the assumption that all scientific laws and theories are valid until a counterexample is observed. If a good quality verifiable experiment contradicts a well-established law or theory, then the law or theory must be modified or overthrown completely. The study of science in general, and physics in particular, is an adventure much like the exploration of an uncharted ocean. Discoveries are made, models, theories, and laws are formulated, and the beauty of the physical universe is made more sublime for the insights gained. 1.2 Units and Standards, Learning Objectives. By the end of this section, you will be able to describe how SI base units are defined, describe how derived units are created from base units, express quantities given in SI units using metric prefixes. As we saw previously, the range of objects and phenomena studied in physics is immense. From the incredibly short lifetime of a nucleus to the age of the Earth, from the tiny sizes of subnuclear particles to the vast distance to the edges of the known universe, from the force exerted by a jumping flea to the force between Earth and the Sun, there are enough factors of 10 to challenge the imagination of even the most experienced scientist. Giving numerical values for physical quantities and equations for physical principles allows us to understand nature much more deeply than qualitative descriptions alone. To comprehend these vast ranges, we must also have accepted units in which to express them. We shall find that even the potentially mundane discussion of meters, kilograms, and seconds, a profound simplicity of nature appears. All physical quantities can be expressed as combinations of only 7 base physical quantities. We define a physical quantity either by specifying how it is measured or by stating how it is calculated from other measurements. For example, we might define distance and time by specifying methods for measuring them, such as using a meter stick and a stopwatch. Then we could define average speed by stating that it is calculated as a total distance traveled divided by the time of travel. Measurements of physical quantities are expressed in terms of units, which are standardized values. For example, the length of a race, which is a physical quantity, can be expressed in units of meters or kilometers. Without standardized units, it would be extremely difficult for scientists to express and compare measured values in a meaningful way. 2 major systems of units are used in the world: SI units and English units. Metric system and the English units. English units were historically used in nations once ruled by the British Empire and are still widely used in the United States. English units may also be referred to as the foot-pound second system, as opposed to the centimeter-gram second system. You may also encounter the term SAE units, named after the Society of Automotive Engineers. Products such as fasteners and automotive tools that are measured in inches rather than metric units are referred to as SAE fasteners or SAE wrenches. Virtually every other country in the world now uses SI units as the standard. The metric system is also the standard system agreed on by scientists and mathematicians. SI units, base and derived units. In any system of units, the units for some physical quantities must be defined through a measurement process. These are called the base quantities for that system, and their units are the system's base units. All other physical quantities can then be expressed as algebraic combinations of the base quantities. Each of these physical quantities is then known as a derived quantity, and each unit is called a derived unit. The choice of the base quantities is somewhat arbitrary, as long as they are independent of each other and all other quantities can be derived from them. Typically, the goal is to choose physical quantities that can be measured accurately to a high precision as the base quantities. The reason for this is simple. Since the derived units can be expressed as algebraic combinations of the base units, they can only be as accurate and precise as the base units from which they are derived. Based on such considerations, the International Standard Organization recommends using 7 base quantities, which form the International System of Quantities. These are the base quantities used to define the SI base units. Table 1.1 lists these 7 ISQ base quantities and the corresponding SI base units. Oh, wow. I wonder, I was feeling not so great. Drains 3250. That means over 3 liters of fluid was in there. Okay. You're probably already familiar with some derived quantities that can be formed from the base quantities in Table 1.1. For example, the geometric concept of area is always calculated as the product of 2 lengths. Thus, area is a derived quantity that can be expressed in terms of SI base units using square meters. Similarly, volume is a derived quantity that can be expressed in cubic meters. Speed is length per time, so in terms of SI base units, we could measure it in meters per second. Volume mass density is mass per volume, which is expressed in terms of SI base units such as kilograms per cubic meter. Angles can also be thought of as derived quantities because they can be defined as the ratio of the arc length subtended by 2 radii of a circle to the radius of the circle. This is how the radian is defined. Depending on your background and interests, you may be able to come up with other derived quantities such as the mass flow rate or volume flow rate of a fluid, electric charge, mass flux density, and so on. We will see many more examples throughout this text. For now, the point is that every physical quantity can be derived from the 7 base quantities in Table 1.1, and the units of every physical quantity can be derived from the 7 SI base units. For the most part, we use SI units in this text. Non-SI units are used in a few applications in which they are in very common use, such as the measurement of temperature in degrees Celsius, the measurement of fluid volume in liters, and the measurement of energies of elementary particles in electron volts. Whenever non-SI units are discussed, they are tied to SI units through conversions. For example, 1 liter is 10 to the negative 3 meters cubed. Units of time, length, and mass. The second, meter and kilogram. The initial chapters in this textbook are concerned with mechanics, fluids, and waves. In these subjects, all pertinent physical quantities can be expressed in terms of the base units of length, mass, and time. Therefore, we now turn to a discussion of these 3 base units, leaving discussion of the others until they are needed later. The second. The SI unit for time, the second, has a long history. For many years, it was defined as 1 over 86,400 of a mean solar day. More recently, a new standard was adopted to gain greater accuracy and to define the second in terms of a non-varying or constant physical phenomenon. Cesium atoms can be made to vibrate in a very steady way, and these vibrations can be readily observed and counted. In 1967, the second was redefined as the time required for 9,192,631,773 of vibrations to occur. Note that this may seem like more precision than you would ever need, but it isn't. GPSs rely on the precision of atomic clocks to be able to give you turn-by-turn direction on the surface of the Earth, far from the satellites broadcasting their location. The meter. The SI unit for the length is the meter. Its definition has also changed over time to become more precise. The meter was first defined in 1791 as 1/10 millionth of the distance from the equator to the North Pole. This measurement was improved in 1889 by redefining the meter to be the distance between 2 engraved lines on a platinum iridium bar now kept near Paris. By 1960, it had become possible to define the meter even more accurately in terms of the wavelength of light. So it was again redefined as 1,650,763.73 wavelengths of orange light emitted by krypton atoms. In 1983, the meter was given its current definition as the distance light travels in a vacuum at 299,792,458 of a second. This change came after knowing the speed of light to be exactly 299,792,458 meters per second. The length of the meter will change if the speed of light is someday measured with greater accuracy. All right, a kilogram. The SI unit for mass is the kilogram. Sorry. All right. From 1795 to 2018, it was defined to be the mass of a platinum iridium cylinder kept with the old meter standard at the International Bureau of Weights and Measures near Paris. However, this cylinder has lost roughly 50 micrograms since it was created. Because this is the standard, this has shifted how we define a kilogram. Therefore, a new definition was adopted in May 2019 based on the Planck constant and other constants which will never change in value. We will study Planck's constant in quantum mechanics, which is an area of physics that describes how the smallest pieces of the universe work. The kilogram is measured on a Kibble balance. When a weight is placed on a Kibble balance, an electrical current is produced that is proportional to Planck's constant. Since Planck's constant is defined, the exact current measurements in the balance define a kilogram. Metric prefixes. SI units are part of the metric system, which is convenient for scientific and engineering calculations because the units are categorized by factors of 10. Table 1.2 lists the metric prefixes and symbols used to denote various factors of 10 in SI units. For example, a centimeter is 1/100th of a meter, and a kilometer is 1,000 meters. Similarly, a megagram is 1,000,000 grams, a nanosecond is 1/1000th of a second, and a terameter is 1,000,000,000,000 meters. The only rule when using metric prefixes is that you cannot double them up. For example, if you have measurements in petameters, it is not proper to talk about megagigameters. Although 10 times 10 to the 6 times 10 to the 9 is 10 to the 15. In practice, the only time this becomes a bit confusing is when discussing masses. As we have seen, the base SI unit of mass is the kilogram, but metric prefixes need to be applied to the gram. Because we are not allowed to double up prefixes, thus 1,000 kilograms is written as a megagram. Since 10 to the 3 kilograms equals 10 to the 3 times 10 to the 3 grams equals 10 to the 6 grams equals 1 megagram. Incidentally, 10 to the 3 kilograms is also called a metric ton, abbreviated T. This is one of the units outside the SI system considered acceptable for use with SI units. As we see in the next section, metric systems have the advantage that conversions of units involve only powers of 10. There are 100 centimeters in a meter, 1,000 meters in a kilometer, and so on. In non-metric systems, such as the English system of units, the relationships are not as simple. There are 12 inches in 1 foot, 5,280 feet in 1 mile, and so on. Another advantage of metric systems is that the same unit can be used over extremely large ranges of values simply by scaling it with an appropriate metric prefix. The prefix is chosen by the order of magnitude of physical quantities commonly found in the task at hand. For example, distances in meters are suitable in construction, whereas distances in kilometers are appropriate for air travel, and nanometers are convenient in optical design. With the metric system, there is no need to invent new units for particular applications. Instead, we rescale the units with which we are already familiar. One point three, unit conversion. Learning objectives. By the end of this section, you will be able to use conversion factors to express the value of a given quantity in different units. It is often necessary to convert from one unit to another. For example, if you are reading a European cookbook, some quantities may be expressed in units of liters, and you need to convert them to cups. Or perhaps you are reading some walking directions from one location to another, and you are interested in how many miles you will be walking. In this case, you may need to convert units of feet or meters to miles. Let's consider this simple example of how to convert units. Feet or meters to miles. Suppose we want to convert 80 meters to kilometers. The first thing to do is list the units you want to have, or the units you have, and the units to which you want to convert. In this case, we have units in meters and we want to convert to kilometers. Next, we need to determine a conversion factor relating meters to kilometers. A conversion factor is a ratio that expresses how many of one unit are equal to another unit. For example, there are 12 inches in 1 foot, 1,609 meters in 1 mile, and 100 centimeters in 1 meter, 60 seconds in 1 minute, and so on. Refer to Appendix B for a more complete list of conversion factors. In this case, we know that there are 1,000 meters in 1 kilometer. Now we can set up our unit conversion. We write the units we have and then multiply them by the conversion factor so the units cancel out as shown. Okay. Note that the unwanted meter units cancel out, leaving only the desired kilometer unit. You can use this method to convert between any type of unit. Now the conversion of 80 meters to kilometers is simply the use of a metric prefix, as we saw in the preceding section. So we can get the same answer just as easily by noting that 80 meters equals 8.0 times 10 to the 1 meters equals 8.0 times 10 to the negative 2 kilometers equals 0.080 kilometers. Since kilo means 10 to the 3, and 1 equals negative 2 plus 3. However, using conversion factors is handy when converting between units that are not metric and when converting between derived units, as the following examples illustrate. Unit conversions may not seem very interesting, but not doing them can be costly. One famous example of this situation was seen with the Mars Climate Orbiter. This probe was launched by NASA on December 11, 1998. On September 23, 1999, while attempting to guide the probe into its planned orbit around Mars, NASA lost contact with it. Subsequent investigation showed a piece of software called SM Forces was recording thruster performance data in the English units of pound-seconds. However, other pieces of software that use these values for course corrections expected them to be recorded in the SI units of Newton-seconds, as dictated in the software interface protocols. This error caused the probe to follow a very different trajectory from what NASA thought it was following, which most likely caused the probe either to burn up in the Martian atmosphere or to shoot out into space. This failure to pay attention to unit conversions cost hundreds of millions of dollars, not to mention all the time invested by the scientists and engineers who worked on the project. 1.4, dimensional analysis. Learning objectives. By the end of this section, you will be able to Find the dimensions of a mathematical expression involving physical quantities. Determine whether an equation involving physical quantities is dimensionally consistent. A dimension of any physical quantity expresses its dependence on the base quantities as a product of symbols, representing the base quantities. Table 1.3 lists the base quantities and the symbols used for their dimension. For example, a measurement of length is said to have dimension L or L to the first. A measurement of mass has dimension M or M to the first, and a measurement of time has dimension T or T to the first. Like units, dimensions obey the rules of algebra. Thus, area is the product of two lengths and so has dimension L squared, or length squared. Similarly, volume is the product of three lengths and has dimension L cubed, or length cubed. Speed has dimension length over time, L over T, or L T to the negative 1. Volumetric mass density has dimension M per L3, or ml to the negative 3, or mass over length cubed. In general, the dimension of any physical quantity can be written as L to the A, M to the B, T to the C, I to the D, that's theta to the E, N to the F, J to the G, for some powers A, B, C, D, E, F, and G. We can write the dimensions of a length in this form with A equals 1 and the remaining 6 powers all set equal to 0. L equals L to the 1, M to the 0, T to the 0, I to the 0, theta to the 0, N to the 0, J to the 0. Any quantity with a dimension that can be written so that all 7 powers are 0 is called dimensionless. Physicists often call dimensionless quantities pure numbers. Take a little peek at that real quick. Physicists often use square brackets around the symbol for a physical quantity to represent the dimensions of that quantity. For example, if r is the radius of a cylinder and h is its height, then we write r equals L and h equals L to indicate the dimensions of the radius and height are both of those length, or L. Similarly, if we use the symbol A for surface area of a cylinder and V for its volume, then A equals L squared and V equals L cubed. If we use the symbol M for the mass of a cylinder and rho, the density of the material from which the cylinder is made, then M equals M and rho equals ML to the negative third. The importance of the concept of dimension arises from the fact that any mathematical equation relating physical quantities must be dimensionally consistent. This means that the equation must obey the following rules. Every term in an expression must have the same dimensions and does not make sense to add or subtract quantities or differing dimensions. Thinking in particular, the expressions on each side of the equality in an equation must have the same dimensions. The arguments of any standard mathematical function, such as trigonometric functions, logarithms, or exponential functions that appear in the equation must be dimensionless. These functions require pure numbers as inputs and give pure numbers as outputs. If either of these rules is violated, an equation is not dimensionally consistent and cannot possibly be a correct statement of physical law. This simple fact can be used to check for typos or algebra mistakes, to help remember the various laws of physics, and even to suggest the forms that new laws of physics might take. This last use of dimensions is beyond the scope of this text, but is something you will undoubtedly learn later in your academic career. 1.5. Estimates and Fermi calculations. Learning objectives. By the end of this section, you will be able to estimate the values of physical quantities. On many occasions, physicists, other scientists, and engineers need to make estimates for a particular quantity. Other terms sometimes used are guesstimates, order of magnitude approximations, back of the envelope calculations, or Fermi calculations. Will that piece of equipment fit in the back of the car, or do we need to rent a truck? How long will this download take? And about how large a current will there be in this circuit when it is turned on? How many houses could a proposed power plant actually power if it is built? Note that estimating does not mean guessing a number or a formula at random. Rather, estimation means using prior experience and sound physical reasoning to arrive at a rough idea of a quantity's value. Because the process of determining a reliable approximation usually involves the identification of correct physical principles and a good guess about the relevant variables, estimating is very useful in developing physical intuition. Estimates also allow us to perform sanity checks on calculations or policy proposals by helping us to rule out certain scenarios or unrealistic numbers. They allow us to challenge others in our efforts to learn truths about the world. Many estimates are based on formulas in which the input quantities are known only to a limited precision. As you develop physics problem-solving skills, you will also develop skills at estimating. You develop these skills by thinking more quantitatively and by being willing to take risks. As with any skill, experience helps. Familiarity with dimensions and units and the scales of base quantities also helps. To make some progress in estimating, you need to have some definite ideas about how variables may be related. The following strategies may help you in practicing the art of estimation. Get big lengths from smaller lengths. When estimating lengths, remember that anything can be a ruler. Thus imagine breaking a big thing into smaller things. Estimate the length of one of the smaller things and multiply to get the length of the big thing. For example, to estimate the height of a building, first count how many floors it has. Then estimate how big a single floor is by imagining how many people would have to stand on each other's shoulders to reach the ceiling. Last, estimate the height of a person. The product of these three estimates is your estimate of the height of the building. It helps to have memorized a few length scales relevant to the sorts of problems you might find yourself solving. For example, knowing some of the length scales in Figure 1.4 might come in handy. Sometimes it also helps to do this in reverse. That is, to estimate the length of a small thing, imagine a bunch of them making up a bigger thing. For example, the estimate to estimate the thickness of a sheet of paper, estimate the thickness of a stack of paper, and then divide by the number of pages on the stack. These same strategies of breaking big things into smaller things or aggregating smaller quantities or smaller things into a bigger thing can sometimes be used to estimate other physical quantities, such as masses and times. Get areas and volumes from lengths. When dealing with an area or a volume of a complex object, introduce a simple model of the object, such as a sphere or a box. Then estimate the linear dimensions first and use your estimates to obtain the volume or area from standard geometric formulas. If you happen to have an estimate of an object's area or a volume, you can also do the reverse. That is, use standard geometric formulas to get an estimate of its linear dimensions. Get masses from volumes and densities. When estimating masses of objects, it can help to first estimate its volume and then estimate its mass from a rough estimate of its average density. For this, it helps to remember that the density of air is around 1 kilogram per meter cubed. The density of water is 10 to the third kilograms per meter cubed. And the densest everyday solids max out at around 10 to the 4 kilograms per meter cubed. Asking yourself whether an object floats or sinks in either air or water gets you a ballpark estimate of its density. You can also do this the other way around. If you have an estimate of an object's mass and its density, you can use them to get an estimate of its volume. If all else fails, bound it. For physical quantities for which you do not have a lot of intuition, sometimes the best you can do is think something like, well, it must be bigger than this and smaller than that. For example, suppose you need to estimate the mass of a moose. Maybe you have a lot of experience with moose and know their average mass offhand. If so, great. But for most people, the best they can do is to think something like, it must be bigger than a person and less than a car. If you need a single number for a subsequent calculation, you can take the geometric mean of the upper and lower bound, that is, if you multiply them together and then take the square root. For the moose mass example, this would be 10 squared times 10 to the cubed, 10 cubed, all quantity to the half power equals 10 to the 2 and a half power equals 10 to the half power times 10 to the 2 power equals 3 times 10 to the 2 power. The tighter the bounds, the better. Also, no rules are unbreakable when it comes to estimation. If you think the value of the quantity is likely to be closer to the upper bounds than the lower bounds, then you may want to bump up your estimate from the geometric mean by an order or two of magnitude. One significant figure is fine. There is no need to go beyond one significant figure when doing calculations to obtain an estimate. In most cases, the order of magnitude is good enough. The goal is just to get in the ballpark figure, so keep the arithmetic as simple as possible. Ask yourself, does this make any sense? Last, check to see whether your answer is reasonable. How does it compare with the values of other quantities with the same dimensions that you already know or can look up easily? If you get some wacky answer, first check to see whether your units are correct. Then check for arithmetic errors, then rethink the logic you used to arrive at your answer. If everything checks out, you may have just proved that some slick new idea is actually bogus. How many piano tuners are there in New York City? How many leaves are on that tree? If you are studying photosynthesis or thinking of writing a smartphone app for piano tuners, then the answer to these questions might be of great interest to you. Otherwise, you probably couldn't care less what the answers are. However, these are exactly the sorts of estimation problems that people in various tech industries have been asking potential employees to evaluate their quantitative reasoning skills. If building physical intuition and evaluating quantitative claims do not seem like sufficient reasons for you to practice estimation problems, how about the fact that being good at them just might land you a high-paying job? 1.6 Significant figures. Learning objectives. By the end of this section, you will be able to determine the correct number of significant figures for the results of a computation, describe the relationship between the concepts of accuracy, precision, uncertainty, and discrepancy, calculate the percent uncertainty of a measurement given its value and its uncertainty, determine the uncertainty of a result of a computation involving quantities with given uncertainties. Figure 111 shows two instruments used to measure the mass of an object. The digital scale has mostly replaced the double pan balance in physics labs because it gives more accurate and precise measurements. But what exactly do we mean by accurate and precise? Aren't they the same thing? In this section, we examine in detail the process of making and reporting a measurement. Accuracy and precision of a measurement. Science is based on observation and experiment, that is, on measurements. Accuracy is how close a measurement is to the accepted reference value for that measurement. For example, let's say we want to measure the length of standard printer paper. The packaging in which we purchase the paper states that it is 11 inches long. We then measure the length of the paper 3 times to obtain the following measurements: 11.1 inches, 11.2 inches, 10.9 inches. These measurements are quite accurate because they are very close to the reference value of 11. In contrast, if we had obtained a measurement of 12, our measurement would not be very accurate. Notice that the concept of accuracy requires that an accepted reference value be given. The precision of measurements refers to how close the agreement is between repeated independent measurements. Consider the example of the paper measurements. The precision of the measurements refers to the spread of the measured values. One way to analyze the precision of the measurements is to determine the range, or difference, between the lowest and the highest measured values. In this case, the lowest value is 10.9 inches and the highest value is 11.2 inches. Thus, the measured values deviated from each other by at most 0.3 inches. These measurements were relatively precise because they did not vary much in value. However, if the measured values had been 10.9 inch, 11.1 inch, and 11.9 inch, then the measurements would not be very precise because there would be significant variation from one measurement to another. Notice that the concept of precision depends only on the actual measurements required and does not depend on an accepted reference value. The measurements in the paper example are both accurate and precise, but in some cases, measurements are accurate but not precise, or they are precise but not accurate. Let's consider an example of a GPS attempting to locate the position of a restaurant in a city. Think of the restaurant location as existing at the center of the bullseye's mark, and think of each GPS's attempt to locate the restaurant as a black dot. In figure 1.12a, we see the GPS measurements are spread out far apart from each other, but they are all relatively close to the actual location of the restaurant at the center of the target. This indicates a low precision, high accuracy measuring system. However, in figure 1.12b, the GPS measurements are concentrated quite closely to one another, but they are far away from the target location. This indicates a high precision, low accuracy measuring system. Accuracy, precision, uncertainty, discrepancy. The precision of a measuring system is related to the uncertainty in the measurements, whereas the accuracy is related to the discrepancy from the accepted reference value. Uncertainty is a quantitative measure of how much your measured values deviate from one another. There is many different methods of calculating uncertainty, each of which is appropriate to different situations. Some examples include taking the range, or finding the standard deviation of the measurements. Discrepancy is the difference between the measured value and a given standard or expected value. If the measurements are not very precise, then the uncertainty of the values is high. If the measurements are not very accurate, then the discrepancy of the values is high. Recall our example of measuring paper length. We obtained measurements of 11.1, 11.2, and 10.9 inches, and the accepted value was 11 inches. We might average the three measurements to say our best guess is 11.1 inch. In this case, our discrepancy is 11.1 minus 11.0 equals 0.1 inches, which provides a quantitative measure of accuracy. We might calculate the uncertainty in our best guess by using half of the range of our measured values, 0.15 inches. Then we would say that the length of the paper is 11.1 inches, plus or minus 0.15 inches. The uncertainty in a measurement, A, is often denoted as sigma A or delta A, so the measurement result would be recorded as A plus or minus delta A. Returning to our paper example, the measured length of the paper could be expressed as 11.1 plus or minus 0.15 inches. Since the discrepancy of 0.1 inches is less than the uncertainty of 0.15 inches, we might say that the measured value agrees with the accepted reference value with an experimental uncertainty. Some factors that contribute to uncertainty in a measurement include the following: limitations of the measuring device, the skill of the person taking the measurement, irregularities in the object being measured, other factors that affect the outcome. In our example, such factors contributed to the uncertainty could be the smallest division on the ruler is 1/16 inches. The person using the ruler has bad eyesight, the ruler is worn down on one end, or one side of the paper is slightly longer than the other. At any rate, the uncertainty in a measurement must be calculated to quantify its precision. If a reference value is known, it makes sense to calculate the discrepancy as well as to quantify the accuracy. Percent uncertainty. Another method of expressing uncertainty is as a percent of the measured value. If a measured value A or measurement A is expressed with uncertainty delta A, percent uncertainty is defined as percent uncertainty equals delta A over A times 100. Uncertainties in calculations. Uncertainty exists in anything calculated from measured quantities. For example, the area of a floor calculated from measurements of its length and width has an uncertainty because the length and width have uncertainties. How big is the uncertainty in something you calculate by multiplication or division? If the measurement going into the calculation have smaller uncertainties, then the method adding percents can be used for multiplication or division. This method states that the percent uncertainty in the quantity calculated by multiplication or division is the sum of the percent uncertainties in the items used to make the calculation. For example, if a floor has a length of 4 meters and a width of 3 meters, with uncertainties of 2% and 1% respectively, then the area of the floor is 12.0 meters squared and has an uncertainty of 3%. Precision of measuring tools and significant figures. An important factor in the precision of measurements involves the precision of the measuring tool. In general, a precise measuring tool is one that can measure values in very small increments. For example, a standard ruler can measure length to the nearest millimeter, whereas a caliper can measure length to the nearest 0.01 millimeter. A caliper is a more precise measuring tool because it can measure extremely small differences in the length. The more precise the measuring tool, the more precise the measurement. When we express measured values, we can only list as many digits as we measured initially with our measuring tool. For example, if we have a standard ruler to measure length of a stick, we may measure it to be 36.7 centimeters. We can't express this value as 36.71 because our measuring tool is not precise enough to measure 1/100th of a centimeter. It should be noted the last digit in a measured value can be estimated in some way by the persons performing the measurement. For example, the person measuring the length of a stick with a ruler notices that the stick seems to be somewhere in between 3.66 and 3.67 centimeters, and he or she must estimate the value of the last digit. Using the method of significant figures, the rule is that the last digit written down in a measurement is the first digit with some uncertainty. To determine the numbers of significant digits in a value, start with the first measured value at the left and count the numbers of digits through the last digit written on the right. For example, the measured value 36.7 centimeters has 3 digits, or 3 significant figures. Significant figures indicate the precision of the measuring tool used to measure a value. Zeros. Special consideration is given to zeros when counting significant figures. The zeros in 0.053 are not significant because they are placeholders that locate the decimal point. There are 2 significant figures in 0.053. The zeros in 10.053 are not placeholders. They are significant. This number has 5 significant figures. The zeros in 1300 may or may not be significant. Depending on the style of writing numbers, they could mean the number is known to the last digit, or they could be placeholders. So 1300 could have 2, 3, or 4 significant figures. To avoid this ambiguity, we should write 1300 in scientific notation as 1.3 times 10 to the 3, 1.30 times 10 to the 3, or 1.300 times 10 to the 3, depending on whether it has 2, 3, or 4 significant figures. Zeros are all significant except when they serve only as placeholders. Significant figures and calculations. When combining measurements with different degrees of precision, the number of significant digits in the final answer can be no greater than the multiplication and division of significant digits and the least precise measured value. There are 2 different rules, one for multiplication and division, and the other for addition and subtraction. For multiplication and division, the result should have the same number of significant figures as the quantity with the least number of significant figures entering into the calculation. For example, the area of a circle can be calculated from its radius using A equals pi r squared. Let's see how many significant figures the area of if the radius has only say r equals 1.2 meters. Using the calculator with an 8-digit output, we would calculate A equals pi r squared, which equals 3.1415927 ellipses, times 1.2 meters squared, 1.2 squared meters squared, equals 4.52838,934 meters squared. But because the radius has only 2 significant figures, it limits the calculated quantity to 2 significant figures, or A equals 4.5 meters squared. Although pi is good to at least 8 digits. For addition and subtraction, the answer can contain no more decimal places than the least precise measurement. Suppose we buy 7.56 kilograms of potatoes in the grocery store as measured with a scale with precision 0.01 kilograms. Then we drop off 6.052 kilograms of potatoes at your laboratory as measured by a scale with precision 0.001 kilograms. Then we go home and add 13.7 kilograms of potatoes as measured by a bathroom scale with precision 0.1 kilograms. How many kilograms of potatoes do we now have, and how many significant figures are appropriate in the answer? The mass is found by simple addition and subtraction. 7.56 kilograms minus 6.052 kilograms equals 13.7 kilograms. Plus 13.7 kilograms. That equals 15.208 kilograms, which rounds to 15.2. Next, we identify the least precise measurement, 13.7 kilograms. This measurement is expressed to the 0.1 decimal place, so our final answer must also be expressed to the 0.1 decimal place. Thus, the answer is rounded to the 10th place, giving us 15.2 kilograms. significant figures in this text. In this text, most numbers are assumed to have 3 significant figures. Furthermore, consistent numbers of significant figures are used in all worked examples. An answer given to 3 digits is based on input good to at least 3 digits. For example, if the input has fewer significant figures, the answer will also have fewer significant figures. Care is also taken that the number of significant figures is reasonable to the situation posed. In some topics, particularly in optics, more accurate numbers are needed, and we use more than 3 significant figures. Finally, if a number is exact, such as the 2 in the formula for the circumference of a circle, c equals 2 pi r, it does not affect the number of significant figures in a calculation. Likewise, conversion factors such as 100 centimeters per 1 meter are considered exact and do not affect the number of significant figures in a calculation. 1.7. Solving problems in physics. Learning objectives. By the end of this section, you will be able to describe the process for developing a problem-solving strategy, explain how to find the numerical solution to a problem, summarize the process for assessing the significance of the numerical solution to a problem. Problem-solving skills are clearly essential to success in a quantitative course in physics. More important, the ability to apply broad physical principles, usually represented by equations, to specific situations is a very powerful form of knowledge. It is much more powerful than memorizing a list of facts. Analytical skills and problem-solving abilities can be applied to new situations, whereas a list of facts cannot be made long enough to contain every possible circumstance. Such analytical skills are useful both for solving problems in this text and for applying physics in everyday life. As you are probably well aware, a certain amount of creativity and insight is required to solve problems. No rigid procedure works every time. Creativity and insight grow with experience. Hold on. I lost my place. I have to start over because I don't know where I left off. I can't see the word. I thought I said experience, but I don't see that word anywhere. So problem-solving skills are clearly essential to success in a quantitative course in physics. More important, the ability to apply broad physical principles, usually represented by equations, to specific situations is a very powerful form of knowledge. It is much more powerful than memorizing a list of facts. Analytical skills and problem-solving abilities can be applied to new situations, whereas a list of facts cannot be made long enough to contain every possible circumstance. Such analytical skills are useful both for solving problems in this text and for applying physics in everyday life. As you are probably well aware, a certain amount of creativity and insight is required to solve problems. No rigid procedure works every time. Creativity and insight grow with experience. With practice, the basics of problem solving become almost automatic. One way to get practice is to work out the text examples for yourself as you read. Another is to work as many end-of-section problems as possible, starting with the easiest to build confidence and then progressing to the more difficult. After you become involved in physics, you will see it all around you, and you can begin to apply it to situations you encounter outside the classroom, just as is done in many of the applications in this text. Although there is no simple step-by-step method that works for every problem, the following 3-stage process facilitates problem solving and makes it more meaningful. The 3 stages are strategy, solution, and significance. This process is used in examples throughout the book. Here we look at each stage of the process in turn. Strategy. Strategy is the beginning stage of solving a problem. The idea is to figure out exactly what the problem is and then develop a strategy for solving it. Some general advice for this stage is as follows. Examine the situation to determine which physical principles are involved. It often helps to draw a simple sketch at the outset. You often need to decide which direction is positive, and note that on your sketch, when you have identified the physical principles, it is much easier to find and apply the equations representing those principles. Although finding the correct equation is essential, keep in mind that equations represent physical principles, laws of nature, and relationships among physical quantities. Without a conceptual understanding of a problem, a numerical solution is meaningless. Make a list of what is given or can be inferred from the problem as stated. Many problems are stated very succinctly and require some inspection to determine what is known. Drawing a sketch can be very useful at this point as well. Formally, identifying the knowns is of particular importance in applying physics to real-world situations. For example, the word stopped means the velocity is zero at that instant. Also, we can take the initial time and position as zero by the appropriate choice of coordinate system. Identify exactly what needs to be determined in the problem. In complex problems, especially, it is not always obvious what needs to be found or in what sequence. Making a list can help identify the unknowns. Determine which physical principles can help you solve the problem. Since physical principles tend to be expressed in the form of mathematical equations, a list of knowns and unknowns can help here. It is easiest if you can find equations that contain only one unknown, that is, all the other variables are known, so you can solve for the unknown easily. If the equation contains more than one unknown, then additional equations are needed to solve the problem. In some problems, several unknowns must be determined to get at the one needed most. In such problems, it is especially important to keep physical principles in mind to avoid going astray in the sea of equations. You may have to use two different equations to get the final answer. Solution. The solution stage is when you do the math. Substitute the knowns into the appropriate equation and obtain numerical solutions complete with units. That is, do the algebra, calculus, geometry, or arithmetic necessary to find the unknown from the knowns, being sure to carry the units through the calculations. This step is clearly important because it produces the numerical answer along with its units. Notice, however, that this stage is only 1/3 of the overall problem-solving process. Significance. After having done the math in the solution stage of the problem solving, it is tempting to think you are done. But always remember that physics is not math. Rather, in doing physics, we use mathematics as a tool to help us understand nature. So after you obtain a numerical answer, you should always assess its significance. Check your units. If the units of the answer are incorrect, then an error has been made and you should go back over your previous steps to find it. One way to find the mistake is to check all the equations you derived for dimensional consistency. However, be warned that correct units do not guarantee the numerical part of the answer is also correct. Check the answer to see whether it is reasonable. Does it make sense? This step is extremely important. The goal of physics is to describe nature accurately. To determine whether the answer is reasonable, check both its magnitude and its sign. In addition to its units, the magnitude should be consistent with a rough estimate of what it should be. It should also compare reasonably with magnitudes of other quantities of the same type. The sign usually tells you about direction and should be consistent with your prior expectations. Your judgment will improve as you solve more physics problems, and it will become possible for you to make finer judgments regarding whether nature is described adequately by the answer to a problem. This step brings the problem back to its conceptual meaning. If you can judge whether the answer is reasonable, you have a deeper understanding of physics than just being able to solve a problem mechanically. Check to see whether the answer tells you something interesting. What does it mean? This is the flip side of the question. Does it make sense? Ultimately, physics is about understanding nature, and we solve physics problems to learn a little something about how nature operates. Therefore, assuming the answer does make sense, you should always take a moment to see if it tells you something about the world that you find interesting. Even if the answer to this particular problem is not very interesting to you, what about the method you used to solve it? Could the method be adapted to answer a question that you do find interesting? In many ways, it is in answering questions such as these that science progresses. And that's the end of Physics 1.